Thank you for joining in, everyone. Today we're going to be carrying on learning about telecommunications. So this is part 2. So let's just do a short recap of everything that we've learned so far. So we've been talking about telecommunications. We've looked at what the internet is, and we've also looked at different types of networks. So we have different types of networks. We classify them as switch networks, and the other set is broadcast networks. So we are going to be focused on switched networks. So we looked at circuit switch networks, packet switch networks, and with packet switch networks we know that there's more subsections to that. You have the virtual circuit network, and you also have the datagram networks. So we'll be focusing on packet switch networks because they are widely used. The internet uses packets to send information. So when you are sending packets, they are going to be delays. So we've looked at the 4 types of delays in the previous episode. So you have the transmission delay, propagation delay. All these delays, we'll try to reduce them. So queuing delay, processing delay, and we all have the equations. And also after that, we looked at the physical layer. So just before that, we looked at the physical layer. So we know the TCP/IP reference model. So I'm going to write it again. So we know this is very important. TCP/IP reference model. So it's a reference model. So there's stages to it. So you have the application. I'm just going to write app. You have the transport layer. After that, you have the internet. Then you have the network access. And then you have finally the physical. So these are the different layers. So let's just put them as layers so we know. So application layer, transport layer, internet, network access. And last episode we looked at the physical layer. It's how to transmit bit stream over the physical medium. So so we've looked at how the physical layer, it uses like wires so to transport the packets. Some of them are they have different types of wires. We have the twisted pair, we have the optic fiber, and the other one was coaxial cable. All of these have different uses, and all of them are designed for different they have different properties. So they make them some of them are cheaper, some of them are more expensive, and there is reasons for that, and we looked at some of those. And then part 2, we looked at how digital data, it goes through the transceiver and then it comes out as digital signal. So you have digital data, you need to make sure that when it goes to the wire, it needs to be certain type of signal. So you need to use a digital transceiver. So why do we do this digital transceiver? Well, that is because of synchronization. We need to model our data in such a way that there won't be timing errors. We need to make it sure that we design in such a way that it can be used to maybe detect if there's been any changes while the signal is went through. So we looked at different types of uh, turning turning the bits into signals. So we know we've done the physical. So I'm just gonna tell you, we have this bit, right? 0 1 0 0 1 1. Okay, you have this data, and you want to send this digital data into digital signal. So you can just do when it's 0 it's just 0, when it's 1 it's high, 0 0 high high. You can just do that. You can just send this as signal. But sometimes there's a downside to this. Maybe it's like long zeros. That could be a problem. We don't like this long constants. So we develop different types of turning it into different types of signals, and we looked at a few. And we looked at all of their pros and cons. Now we're going to move on to the data link layer, or it's called network access. So let me also write that down. Data link layer. Okay, so what is the data link layer? So when you have let's say you have two computers or two direct connections, and you're passing that, okay, it's direct link. You have someone here and then you have someone else here, so it's the direct link. Okay, so we need to make sure when we're sending the data from 1 to 2, we need to make sure some of the things that we're sending, we send it properly. We need to make sure that the data is synchronized. When you're sending 1, it receives 1, and then you're sending 2, it receives 2, and not that it gets lost because it might be out of clock. We need to we need to have flow control. So there should be a flow control. So when you're passing the data, it needs to be able to receive it, and then if it's like getting too much if there's too much data, it can't process it. It needs to tell 1. Okay, and this should also be error detection as well. We can have that in this layer, and also error control. So now we're going to be looking at asynchronous. So asynchronous, what is that? Well, when you're sending data from 1 to 2, you might want to avoid the timing problem. So the timing problem by you send long ones. If you send long ones, then 2 might not have time to respond all at once. So asynchronous is when you send maybe you don't send long uninterrupted streams of bits. You only send maybe 1 at a time, 1 bit at a time. So asynchronous is when you send 1 character at a time. So when it's sending 1 bit, then 2 will receive it, and then it'll start, and then it'll say, okay, now I'm going to wait for a new bit to come, new character to come. So then it reorganizes itself. So that's asynchronous. So how does 2 know that a new bit is going to come? So we're going to now move away from asynchronous because that is very slow, sending one character at a time. So let's move on to the synchronous. So you keep on sending streams, 2 can keep on acknowledging it, and that's how we want to get fast transfer of data. So we're going to look at synchronous data. So synchronous data is when you send a block of bits and it's like a steady stream. It keeps on flowing. There's no start, there's no stop. Okay, so you're sending a bit. Okay, let's say this is a bit. This is your stream. Okay, right now we're looking at synchronous. So you know that you have the header. Okay, and then you have the data. Okay, so this is called control, and this is control. This is the data. Okay, so let me just write it clearly for you. So these are still zeros and ones. Okay, so we shouldn't get confused with that. So let's say this is also the control. Is some zeros and ones to identify, and this is another bit, another character, and that's the data. So this is your stream of bit. So this one is sending to 2. Okay, one is sending to 2. It's sending this stream of code. So how does 2 know when it started? How does 2 know that another character has started? It doesn't. We need to make sure that it can recognize that another character has started. And how does it do that? So we make sure that there's a flag. Okay, flag. This is a flag. Before every new character, there's a flag. What is this flag? Well, the number 2 needs to recognize that this is a flag. So how does it do that? Well, it has this, you can have it your own, but it needs to be something that's very uncommon. So what we do is we do 0, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. When number 2 sees this set of bits, it knows that a new character will come after this. Okay, that's the flag. So you put that there, you put that there. It knows that a new character has started. But sometimes there's a problem. Your data might have this, and then it might think a new character has started, but actually this was the data. So what we do is called bit stuffing. If stuffing, if your data has let's say after every 5 zeros it'll put a 1, so it's every 5 zeros it'll put a 1. So if your data had let's say 0. So after every 5 ones, it'll put a 0. So if your data had 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, or let's just say 1, 2, 3, 1, 2, 3, 4, 5, 6, okay, and 0. So when your code or number 2 sees this, it'll start from 0, 1, 2, 3, 4, 5, 6, just like here. We don't want the second computer to think that this is a flag. So what we do is called bit stuffing. We put after every 5 ones, put 0. Put 0 after every 5 ones. Okay, so here let's just say this after 5 ones, so 0, and then 1, 2, 3, 4, 5, and then you put a 0. Now this is not 6. Okay, now number 2 will see that, okay, this will read it, it'll say, okay, there's no flag, and then when the flag does come, it'll know, okay, this is a flag. But when it's decoding, it needs to make sure that when it sees this 5 ones, it needs to remove that 0. Okay, it needs to remove that 0 because the 0 wasn't there originally, so it needs to remove it, and that's the original code. Okay, so that is bit stuffing. So we've looked at flags. Now we're going to look at flow control. So let's just wipe this off. Now the transmitter, it puts flags so that the receiver knows that a new character has started. Okay, so it's sending like frames. Now we're going to look at flow control. So what is flow control? So you have a transmitter and is connected to a receiver. So what is the transmitter sending? It's sending frames, and these frames are going to the receiver. What the receiver needs to do is acknowledge these, and it needs to process it. But the transmitter, it might be sending too many, and the receiver can't handle this. So we need to make sure that we have a technique that the receiver doesn't get overwhelmed, because if the receiver gets too much frames, it might need to drop these frames, and that is not good because we're losing data. So if the transmitter is too fast and the receiver is too slow, what can we do? Well, we have a protocol. It's called stop and wait. Stop and wait. So stop and wait, what is that? Well, for stop and wait, we use acknowledgements. After every frame that the transmitter sends, it needs to wait. So the transmitter is waiting for what? For the receiver to send an acknowledgement saying that I have received this, you can now send me the next frame. So for stop and wait, we have a very useful diagram that we use. So I'm going to draw it here. You have the transmitter, you have the receiver. It's sending the frame. Okay, let's say this is frame 1 or frame 0. Now that this is time. Okay, it's going down. This is going down is time. So now that's the frame 0. Now what the receiver needs to do is acknowledge it. Once it received it, processed it, it needs to send a acknowledgement frame. And now what can the transmitter do? It can send the next frame, and it keeps going like that. So this is very simple one. Sending frame, acknowledgement, sending frame, acknowledgement, sending frame. Okay. So there are some downside to this, because transmitter is sending the frame, it sent it, now it's waiting, and then the acknowledgement comes. So what can the transmitter do in the meantime? Well, it's just ideal, it's wasting its time. So what can it do? Well, we have another technique, and that is called the sliding window. So let's just do it right next to it so we can compare later. Sliding window. So with a sliding window, we have that let's say the transmitter, it's sending 8 frames. Okay, so these are the 8 frames. Frame 0, frame 1, frame 2, to frame 8, frame 7. Okay, so we have that it's 8. Okay, it's an 8. So 8 is a very special number. You need how many bits to recognize each frame? So you have frame 0, 1, 2, 3, 4 to 8. You can do how many bits you need to recognize each frame? Well, you need, let's call it K3. You need 3 bits, because 0, 0, 0 would be frame 0, 0, 0, 1 would be frame 1, 0, 0, 0, 1, 0 will be frame 2, like that. So you need 3 bits. Okay, so we call that W. W is 3, and this is very important, because this is the maximum that we can send. So this is the transmitter, this is the receiver. So it can send a maximum of 3. The transmitter can send a maximum of 3. So it will send frame 1, frame 2, frame 3. Now frame 0, frame 1, frame 2. It can send a maximum of 3. It can't send any more. Okay? And why is it not sending any more? Because it has a limit of 3. And now it's waiting for the acknowledgement. The receiver needs to tell it, I have acknowledged these 3, I've got them safely, you can send me the next frames. So where does the sliding window come in? Well, if we go back to this diagram at the top, we've sent how many? We've sent up to F2. Okay, now because it acknowledged that it received 1, 2, 3, the sliding window can move. The sliding window can move, and it can replace the ones that were there before. So F2 is gone, now you have F3 and F4, F5, to F7. You also have, the next frames, F0, right? And now this is moved, is slided. So the transmitter, it sent 3 frames, Now it's waiting, and then it can send another 3, it can send 1 or 2, like that. So the transmitter is doing a lot of work. It's not just sending just 1, wait, 1, wait. It's here, 1, 2, 3, ready. 1, 2, 3, ready. It's more quicker. So there are some pros and cons for this. Let's look at them now. So I hope this diagram makes sense. Now let's look at the performance. The performance of stop and wait. So let's look at all of the delays. What is the total time? And also let's find its utilization, or what is it called? Utility. Okay, let's work that out. So what's the total time? Well, we know that it's transmitting. So it's transmission. And we also have that it's propagating to the receiver. That's T prop. And then what's going to happen? The receiver will process it. So before that, the transmitter, it needs to process it as well, and then the receiver needs to also process it as well. But normally we just say that's very small. We also need to and then we need to process the acknowledgement, and we also need to send the acknowledgement. So we notice that this is 2 because it's processing twice the data, so that's 0, and processing the acknowledgement, that's also 0. So what are we left with? We are left with TTR, that's transmission of the frame, and we are also is propagating, and then the acknowledgement is also propagating as well. So that's 2, 1, 2. Okay, so that's the total time that the frame and the acknowledgement take. That's the total delay, transmission, and then the 2 propagation. So we have this special utilization value that is equal to the transmission delay over the total. And what is the answer for the stop and wait? You just put TR over TR plus 2P, and that simplifies to 1 over 1 plus 2A. What is A? A is the delay in the propagation over the delay in the transmission, and you can put that in there. You can work out the utility. So this is for stop and wait. And the transmission, you should know this already, we looked at it last time. For the transmission, it's the frame size over the data rate. So how much, like the physical medium, what is the data rate of that? And we know that the propagation delay, that is that's equal to distance over speed. Okay, distance over speed, distance of the medium that is traveling over the over the speed, how fast it's traveling. So we should know this, and then we worked out the utilization, and we have some examples that we can go over, but we'll do that later. Let's just right now, let's work it out for the sliding window. So for the sliding window, we have utilization is 1. That is very good. When does this happen? Well, that happens when the window size times by the transmission delay is bigger than or equal to, we had the same here, right? Total TR plus 2 prop. If the window size times by the transmission delay is greater than the transmission plus 2 of the propagation delays. So what does that mean? How does that look like? Well, so we know that W times TR. What is that? Well, we know W is 3, that's here. Okay? That is W times TR. And what is TR plus 2 prop? Well, it's the time that 1 takes. So let's say that 1 F0, the acknowledgement takes this amount of time. So is it bigger? Is W times TR bigger than the acknowledgement of the first frame? No. So U can't be equal to 1. So there's another method. Now we need to work out what U is then, because if it's not 1, if it's not like very, very good, it has to be something else. So what is the equation for that? Well, it's the same equation as this one, but what you need to do is, if this is not true, then you need to work out U by doing W, the window size, over 1 plus 2A. Okay? So that is for sliding window. I hope you understood that. And these equations, we just have to use them. So for the sliding window, you just need to remember, first do this equation, work it out. If you find that W times TR is greater than transmission delay plus 2 propagation delay of the frame, 2 times the propagation delay, if that is true, then U will be 1. But if it's not, then you have to use this equation. Okay? So that was flow control, and that was sliding window. So let's move on now. So we've looked at flow control, we've looked at flags, how it can be synchronized. Now we're going to look at error detection. So first we need to know if there is an error detection. Right? We need to know, how can we work out if there's an error? So you're sending a frame, receiver 2 receives that frame. How can I tell that frame that it received, it didn't get noise added to it. So how can it do that? It needs to find that error. So we have a technique, it's called the CRC algorithm. It's used for, so we've done flow control, it's used for error control. So we'll look at this technique next time, but it's very simple technique and it's very useful. So thank you for listening.